Now, after looking at the mixtures and how we can separate them into distinct or pure substances, we now turn and look at the effects of heat on substances. Heat is a form of energy that causes a change in temperature, and we have defined matter as anything that has mass and occupies space. We have also indicated that matter can exist either as solid, liquid, or gas, and these are the three states of matter which we also said are interconvertible by either heating or cooling. From the chart on your screen, if you heat a solid, it melts into a liquid, a process called melting. Upon further heating, a liquid will evaporate into a gas. If you reverse the process, condensation of a gas results into a liquid, and when a liquid is cooled further, freezing occurs and the liquid is converted into a solid. We also have some substances that transit from solid to gas and vice versa without passing through the liquid phase. Such a process is called sublimation. However, it is important to notice that it is not always that when a solid is heated it will transit through the two phases of liquid and gas. Certain substances decompose upon heating, and we are going to do that in due time. Meanwhile, let us look at the temperature changes during the transition of the three phases. And we shall start with a look at heating of naphthalene. When naphthalene is heated in a boiling tube and temperature recorded at various time intervals, some interesting observations are made. The temperature rises steadily until the solid starts to melt. At this point, it remains constant until all the solid has melted, and then the temperature rises steadily again. Now we can have a sketch of temperature against time for the above information. This is shown on your screen, and we call this a heating curve. So let's try and explain what happens at the various phases. At AB, naphthalene absorbs heat, making the temperature to rise. The absorbed heat increases the kinetic energy of particles so that they vibrate more vigorously. At BC, you realize the temperature is constant. The heat absorbed is used to weaken the forces of attraction holding the particles together, making it to melt, and therefore the temperature does not rise. Rather, temperature remains constant till all the naphthalene has melted. The particles move further apart after the forces of attraction holding them have weakened. At phase CD, the temperature rises steadily again. The liquid naphthalene absorbs more heat, increasing the kinetic energy of particles and thus making them to vibrate more vigorously. A more or less the same curve is obtained when ice is heated up to the gaseous form, that is vapor. Now it will be interesting to note that if the reverse process takes place, a cooling curve is obtained as appears on your screen. Again, you realize on this curve at phase BC, during the state transition, the temperature is again constant. At this point, the forces of attraction between the particles build or strengthen, and the particles draw closer together as the liquid transit into a solid phase. The kinetic theory of matter. The kinetic theory of matter forms the basis of the theoretical model of matter. It states that matter is made up of particles which are in a continuous state of motion. In the solid state, the particles are closely packed together and can only vibrate within fixed positions. The forces of attraction hold the particles together, making it hard for them to move from one point to another. This is the reason why solids have definite shapes. Upon heating, the kinetic energy of particles increase and they begin to vibrate more vigorously. At a temperature called melting point, the forces holding the particles are weakened enough, allowing the particles to change positions, resulting into the solid changing into liquid. In the liquid phase, the particles are farther apart than in solids. They can move from one point to another, explaining why liquids have no definite shape. But still, the particles experience some form of attraction and thus the extent of freedom is limited. And this is why liquids have definite volumes. Upon heating, the kinetic energy of particles increase. They vibrate more vigorously as the forces of attraction weaken. At a temperature called boiling point, the kinetic energy is sufficient to overcome the forces of attraction and the liquid boils as the particles break free to enter into the gaseous phase. In the gaseous phase, the particles are farther apart and they move freely in all directions. The forces of attraction are weakest. This explains why gases have no definite shape nor volume. So if you look at that illustration on your screen, you realize the particles in the solid phase appear to be closely packed and tightly held to each other. They can hardly move from one point to another. On the liquid phase, in the liquid phase, the particles appear to be loosely packed, quite loosely packed, and appear to have some extent of freedom, but still there are forces of attraction holding them together and the extent of freedom is actually limited. However, in the gaseous phase, you realize the particles are farther apart. They appear to have no association to each other, and therefore they move from place to place with a lot of freedom randomly. And that is why gases do not have definite shapes nor volume. Now, upon cooling, the gas particles lose the kinetic energy and they draw closer. The vibrations slow down and the forces of attraction build, forming a liquid, and we say condensation has occurred. Further cooling causes further loss of kinetic energy and the strength of attraction of the forces increase. The vibrations slow down further and the liquid becomes, and we say freezing has taken place. Now notice that melting, boiling, condensation and freezing temperatures are specific for a particular substances. For example, the melting point of water is 0 degrees Celsius while the boiling point is 100 degrees Celsius at sea level. These temperatures are influenced by factors such as altitude and presence of impurities. Freezing and melting occur at the same temperature, that is 0 degrees Celsius for water. Condensation and boiling also occur at the same temperature, that is 100 degrees Celsius for water. And these temperatures are good tests for purity of substances. We now turn an effect of impurities on the melting and boiling points of substances. Now, we have just said that the melting and boiling points of a substance are good indicators of the purity of that substance. Pure water boils at 100 degrees Celsius at sea level and freezes at 0 degrees Celsius. Pure naphthalene has a melting point of 80.2 degrees Celsius. A deviation from these temperatures indicates the presence of impurities. We have also seen that when a substance is melting or boiling, or specifically during transition from one state to another, the temperature remains constant. Recall the graph we drew for the naphthalene. It's again shown on your screen. At phase BC, the temperature is constant and this is the melting point. Now we say that pure substances have sharp boiling and melting points. So we shall start with a look at the effects of these impurities on the melting points of substances, and we shall use the same naphthalene. We have seen that pure naphthalene will melt at 80.2 degrees Celsius. However, if camphor is added to naphthalene as an impurity and heating is done with temperature being recorded at certain time intervals, a different curve is obtained. This is shown on your screen. Now the graph indicates that naphthalene will melt over a range of temperature below 80.2 degrees Celsius. Impure substances do not have sharp melting points. Impurities lower the melting points of substances. This knowledge is applied in clearing snow from roads during winter in temperate regions. When salt is added on the ice, it will melt even at temperatures below 0 degrees Celsius. How about the effects of impurities on the boiling points? When pure water is heated and temperature recorded at time intervals, such a graph is obtained as on your screen. Phase BC is the boiling point. Water boils at 100 degrees Celsius and the boiling point is sharp. However, if salt in the form of sodium chloride is added and the procedure repeated, a different curve is obtained as appears on your screen. Now the boiling point is not sharp and impure water boils over a range of temperature above 100 degrees Celsius. In general, impurities raise the boiling points of substances. Now, in summary, pure substances melt and boil at constant temperatures that are specific for particular substances. Impurities will lower the melting points and raise the boiling points of substances. Melting and boiling points are therefore used to determine the purity of substances. We now turn and look at the temporary and permanent changes that substances undergo when they are heated, and we shall start with temporary physical changes. When zinc oxide is heated, its color changes from white to yellow, and on cooling it reforms back to white. Take a look at this. Similarly, when solid iodine is heated, the shiny dark solid crystals sublime, forming a purple vapor. The vapor on cooling condenses back into the shiny black solids again. Again, take a look at this. Now, those two processes can be represented by the following equations on your screen: that when zinc oxide is heated, it forms a yellow solid of the same zinc oxide. When black solid iodine is heated, it forms a purple vapor of the same iodine, and on cooling, it forms back the black solid crystals. Now, the heating of these substances does not result into any new product being formed, and these are called temporary physical changes, and they have the following features. 1. They are easily reversible. The double arrows indicate that reversibility is possible. There is no new substance formed. There is also no change in mass, and they are not accompanied by heat changes. The next type of a change is what we call temporary chemical changes, and we look at a special type of temporary chemical changes that we call thermal dissociation. When copper 2 sulfate is heated, it changes from blue to white. The blue copper 2 sulfate contains water of crystallization, and it is called the hydrated copper 2 sulfate. When heated, the water evaporates, leaving a white solid that we call anhydrous copper 2 sulfate. Take a look at this. Now, you must have realized that on cooling, the white solid cannot turn back into the blue solid unless water is added. Similarly, when hydrated cobalt 2 chloride is heated, it loses its water of crystallization, turning from pink to blue. The blue solid is called anhydrous cobalt 2 chloride. It cannot turn into pink on cooling unless water is added. Again, take a look at this. Now, the reactions that take place when the two substances are heated are represented by the equations on your screen. You realize that new compounds are formed, and the decomposition of a substance by heat is called thermal dissociation. When water is added to the anhydrous product, a little heat is evolved and the hydrated substances are formed. Heating of copper 2 sulfate and cobalt 2 chloride results into a temporary chemical change, and it has the following features: that a new substance is formed, heat is either evolved or absorbed, there is also a change in mass, and the change is reversible. That is why it is a temporary chemical change. Then we look at permanent chemical changes. When crystals of copper 2 nitrate are heated in a test tube, several observations can be made. That a mixture of gases is produced and a black solid is formed. Take a look at this. When the blue copper 2 nitrate is heated, it first dissolves in its own water of crystallization, and then it boils. A red-brown gas is evolved, and it turns a wet litmus paper red. When a glowing splint is inserted into the boiling tube, it relights, and then we have a black residue that remains. Now, the black solid residue is copper 2 oxide. The wet litmus paper turns red due to presence of nitrogen 4 oxide. The glowing splint is rekindled due to presence of oxygen, and the reaction can be represented by the following equation: that when copper 2 nitrate is heated, it decomposes into copper 2 oxide plus nitrogen 4 oxide plus oxygen. The mass of the product copper 2 oxide is less than that of copper 2 nitrate. Similarly, when heated, potassium manganate 7 decomposes into a black-green solid and a colorless gas is evolved. This gas rekindles a glowing splint. The black-green solid is a mixture of black manganese 4 oxide and green potassium manganate 6. The colorless gas is oxygen. The residue solid weighs less than the original potassium manganate 7, and the decomposition can be represented by the following equation: the decomposition of potassium manganate 7 by heat to form potassium manganate 6, which is green in color, plus manganese 4 oxide, which is black, plus oxygen gas. Now, the decomposition of copper 2 nitrate and potassium manganate 7 are examples of permanent chemical changes, and they have the following features: that new substances are formed, the change is irreversible, there is a change in mass, and heat energy is released or absorbed. Now, away from the effects of heat on substances, we look at the constituents of matter. And we have already indicated that matter can exist either as a mixture or as a pure substance. Pure substances are classified either as elements or compounds. Element is a pure substance that cannot be split further into similar substances by chemical means. Examples of elements include carbon, hydrogen, sulfur, nitrogen, potassium, and many others. Elements are made up of atoms. An atom is the smallest particle of an element that can take part in a chemical reaction. Atoms of the same elements are similar and different from those of other elements. Molecules. Some elements have atoms that cannot exist independently but combine together to form molecules. Examples are hydrogen and oxygen. Others, like sulfur, carbon, and so on, exist singly. A molecule is the smallest particle of an element or a compound that can exist separately. Compounds. Previously, we saw that when iron fillings and sulfur were mixed together, each entity retains its physical properties and can be separated by physical means and easily using a magnet. This was called a mixture. Now, suppose we heat the mixture. You will see that a red glow will spread through the mixture and a black solid is formed. The black solid which is formed is not attracted by a magnet. Both the iron fillings and sulfur lose their original physical properties. Let's take a look at this. So there you have the yellow sulfur and the dark iron fillings. Now when we mix them, we mix the yellow sulfur and the iron fillings. What we have is a mixture of the two, and each retains its physical properties. And we had seen that we can separate the two mixtures by use of a magnet, which will attract the iron fillings. There you have it. And the yellow sulfur will remain behind. It doesn't really become yellow because of the presence of impurities from iron, but you can be sure all the iron fillings have been picked by the magnet. Now that is a mixture. Now we take the mixture and heat. You will see a red glow spread through the mixture. We say that reaction is exothermic. We are heating a mixture of iron fillings and sulfur. There you can see the red glow. The reaction produces a lot of heat, and let's see what product we shall have. So there you have the black solid product that is formed. So let's see its characteristics, let's see its features. It cannot be attracted by the magnet, and both the iron fillings and sulfur have lost their physical properties. Now the black solid is the product of a chemical combination of iron and sulfur. When two or more elements combine chemically, they form. Defined, a compound is a pure substance made up of two or more elements chemically combined. The black compound formed by chemical combination of sulfur and iron is called iron 2 sulfide. By just looking at the name, it is possible to tell which elements have combined to form a compound. For example, magnesium chloride is a compound formed between magnesium and chlorine. Calcium nitride is a compound of calcium and nitrogen. We now turn and look at chemical symbols, and elements in chemistry are represented by letters called chemical symbols. The symbols are usually the first letter of the element's name in English or Latin. However, some elements share the first letters, for example carbon and chlorine. And because of this, some elements have their symbols taking the first letter and another letter from its name. For example, chlorine will be Cl. Important to know is that whenever the chemical symbol has two letters, the first one is always a capital and the second one is always a small letter. Elements with single letters include oxygen with O, nitrogen N, sulfur S, phosphorus P, and carbon C. Elements with two-letter symbols include helium, calcium, magnesium, beryllium, manganese, and so on. Notice that the second letter in the symbol is not necessarily the second letter in the name. For example, if you look at magnesium, the second letter in the name is A. However, in the symbol, the second letter is G. Elements with names derived from Latin include sodium, also called natrium. Lead is called plumbum. Iron is called ferrum. Potassium is called kalium. Copper is called cuprum. Silver is argentum, and gold is aurum. There is no formula for understanding these names and their symbols. You will just have to have them at your fingertips. However, as you get along, it will become a lot easier for you to remember them, especially those that are very frequently mentioned and written. An important thing to know is that whenever in exams you are requested to name a compound or an element, you give the name and not the symbol. When requested to identify, you have the option of giving the chemical symbol or the name. Next is chemical equations. A chemical equation constitutes of two sections separated by an arrow or a pair of arrows. The left-hand side contains the reactants and the right-hand side contains the product. For instance, iron combines with sulfur to form iron 2 sulfide. Iron and sulfur are the reactants, iron 2 sulfide is the product, and this information is represented by the equation as shown on your screen. Now, this is called a word equation. When symbols are used to write the equation, it is called a chemical equation, and we shall look at chemical equations in level 2. The forward arrow indicates that the reaction proceeds in one direction only, it's permanent change and it is irreversible. The twin arrow indicates the reaction can proceed forward or backward directions, it is reversible. The conditions for a reaction are usually indicated on the arrow or below the bottom arrows in case of a twin arrow scenario. For example, iron and sulfur are heated to react, and thus the reaction can be represented with the following word equation. You realize heat is indicated on the arrow. If a catalyst is used in the reaction, it is not part of the reactant. A catalyst is a substance that is used to speed up the rate of a reaction without participating in the reaction. It is not changed. For instance, in the next chapter, we shall see the preparation of oxygen gas by decomposition of hydrogen peroxide. A catalyst in the name of manganese 4 oxide will be used to speed up the reaction, and the equation shall be as shown on your screen, that hydrogen peroxide decomposes into oxygen and water under the catalyst manganese 4 oxide. It is indicated on the arrow and it is not part of the reactant. The manganese 4 oxide will remain the same from the beginning to the end of the reaction.
You can make a bigger difference in the world. You can make a positive change in your career. You can make a greater contribution to the greater good. And you can start today by earning your degree online at Walden University, where advanced degrees advance the quality of life.